Anybody? Okay, so let's thank Sergei again. And the next speaker for this is Sujay Ashok. Are you able to share the screen now, Sujay? Can you try to share your screen?
Try now.
Yeah.
Can you see?
Yeah. Sujay is from Institute of Mathematical Science, and he will tell us about ADS3 cross S1 chiral ring. Yeah.
Thank you. Right. So thank you to Alok and the team at IIT Roorkee for all their hard work. Right, so I'll report on work done with Songyuan Lee and Jan Trost. Jan is my permanent collaborator for the last many years, and Songyuan is his former student who is now a postdoc in Greece, I think. Right, so let me begin with some context for this work. So the context is ADS3 CFT2 for backgrounds that have NS flux. So this is a very well-studied background, especially in the last few years. And a nice review talk by Rajesh about this yesterday. So the approach is sort of powerful because the worldsheet CFT that describes this background with NS flux is exactly solvable in alpha prime. The ADS3 part of the background is described by a Witten model with gauge group SL2R at some level K. And this K sets the scale of the ADS of the curvature in ADS space. So large K essentially amounts to semi-classical gravity. So because we have this powerful worldsheet framework, the idea is to use worldsheet methods to obtain whatever information one can about the bulk ADS3, about strings in ADS3, as well as therefore the dual boundary theory. Okay. So the theories that are best studied have n equals 4,4 supersymmetry, either large or small. And in the last few years has seen an amazing amount of progress, especially due to work by these authors, Day, Bahat, Gebadiel, Kumar, Knighton, and so on. But in this talk, the goal would be to focus on ADS backgrounds with lower supersymmetry, especially 2,2 supersymmetry. So we'll focus on backgrounds that we like to call ADS3, S1, and Y. So I mean, we call it ADS3, S1, and Y, but there are some 4 fermions that make sure that you have n equals 2,2 supersymmetry in spacetime. And the S1, it just takes care of the fact that the 2,2 theory on the boundary has the U1R symmetry in the global algebra. And one can check that this model is a critical string background when the central charge of this compact Y theory takes the form 9 minus 6 pi k. So this K is again the level of the SL2R. So there are various examples one can do. I mean, for instance, if you take Y to be a minimal model, a supersymmetric minimal model, and T4, you get back the n equals 4,4 supersymmetric theories. So we will often check our results by putting this particular Y to make sure that we recover all the known results. But you could just take something like Y to be a sum of 3 minimal models at some levels Ki, such that their inverses add up to 1 by K. So these are all simple examples. But in general, the goal is to see what one can say about such n equals 2 models and how, especially why, how what we compute depends on what in one particular manner. Now, the worldsheet theory on Y has to be, so this is the worldsheet theory. So the worldsheet CFT has to be 2,2 subconformal in order for the space-time theory to have 2,2 supersymmetry. I hope this point is clear. So I'm hoping to describe these space-time or boundary theories with 2,2 supersymmetry. And as a requirement, we need to construct the global superconformal algebra in space-time. And for that, Givion and Pacman back in 2003 showed that this Y model, this worldsheet theory on Y has to have worldsheet 2,2 supersymmetry. So that's the setup that I'll be working with. And what we do is the most elementary thing one can do. We compute the BPS spectrum of the boundary theory or of the bulk theory, if you wish. So these all correspond to space-time. I mean, the boundary CFT operators that are chiral ring elements. So their dimension is determined by this U1R charge. And furthermore, once we do that, we will compute the next simplest thing, which is the structure constants of the chiral ring of these boundaries. And we do this not by computing correlators of the worldsheet CFT, but instead we use the operator product expansion of the worldsheet theory to derive the operator product expansion of space-time. So I mean, I've said lots of CFTs and lots of spacetimes and worldsheets. I hope the idea is clear. I have a 2,2 supersymmetric theory in ADS3 with compact spaces S1 and Y. This is supposedly dual to some holographic theory that lives on the boundary of ADS3, which has 2,2 supersymmetry, superconformal symmetry. And we want to construct the chiral ring of this boundary. And we do that by using this powerful Bezier-Witten model that describes strings in ADS3. Okay, so the slogan is the spacetime OP from the worldsheet OP. Are there any questions at this point? Or clarifications?
Sorry, Sujay, can I ask some?
Yeah.
So there are actually a class of examples. I mean, by taking dihedral orbifolds of D4, which leads to 2,2 SCFTs, and this can be identified with ADS3 cross S3 cross D4, and if you orbifold the S3 cross D4.
Yeah.
I mean, these also have like 2,2. This is some class of examples which were constructed by Matthias, Lawrence, and myself. So
whatever I'm about to say will apply to all 2,2 models, in my opinion.
I see.
It should, because I'm assuming nothing about the compact space. I'm saying all I require is an S1, and Y has to be, CY has to be 9 minus 6 by K. And I'm just saying, what is the most general thing one can say about such models? So it should include all the models.
Yeah, but the examples which we proposed, they didn't have an S1 like explicitly. I mean, so it was like ADS3 cross S3 cross T4, and then the S3 cross T4 is like, say, orbifolded by.
So one should be able to find an 2,2.
Right. Yes.
And I'm saying I can embed it like this.
Okay. Yeah. Okay. Yes.
Yeah. So I'm making no assumptions about what Y is at this point.
Mm-hmm. Okay.
Okay, so I should say that the structure constants for the Foucault-Morpho theories were of course known. They were derived a long time ago by the Butler-Pachman and also Viribey, Pachman, and Vestelli, I think in 2007. So what we do in this work is to compute the structure constants, at least in the sector with no spectral flow, and show really how it depends upon the topological properties of this Y theory. And just to make contact with your previous talks in the conference, this is an example of what in Rajesh's talk was called the easy direction to go from the worldsheet to the space-time. I mean, he's talking about the much harder task of going from space-time to worldsheet. So this is simpler in that respect. Okay, so let's give some details about the worldsheet theory. So the worldsheet theory, like I said, is an SL2R at level K times U1 current algebra times this superconformal theory with 2,2 on Y. The radius of the circle is set by the ADS scale. And what we first need to do is to understand how to describe these chiral ring elements from the worldsheet theory point of view. So we had these boundary conformal dimension and boundary space-time R charges. So these just map to the following eigenvalues of the worldsheet theory. So the J03 eigenvalue of the SL2R maps to this conformal dimension of the boundary theory. And left moving or right moving momentum along the S1 maps to the space-time R charge. So what we need to do is to classify operators based on these charges and just equate H and K. Okay, so boundary chiral ring elements means that you are in the NS sector of the space-time theory. And these can arise from either Nevershots or Ramon sectors of the worldsheet theory. This is the first point. So we start with the very general operator. We have some super ghost fields, bosonic ghost fields, some primary vessel 2R, some momentum mode along the S1, and some operator on Y that I don't know what it is at this moment. Now the SL2R primaries and so on have been very well studied by Givian, Kotosawa, and Seiberg. So we take from them the operator which has an ADS spin equal to small h. So the ADS spin h is precisely the space-time conformal dimension that we're looking for. So we fix that. And if you have fermionic excitations also on the SL2 directions, then this will be changed to H-1, or if you have Raman fields, it can be H-1/2 and so on. But essentially, it is given by the the ADS3 spin. Okay. Then what we do is to demand that I have a chiral primary. So the momentum along the S1 should be equal to this ADS spin up to some proportionality factors. So if you choose an ADS3 spin H element from the SL2R, then you fix immediately the P left to be square root of 2/k times H. Then we have to impose the fact that I have a physical propagating mode, physical propagating spring mode. So you have to set L0 equals half for the superstring or 1 for the bosonic for the matter part. And this will fix the dimension of the operator on Y, again in terms of the ADS3 spin. So what I'm trying to say is that the chiral ring is operator, the worldsheet operator that corresponds to a boundary chiral ring element is completely fixed by the ADS3 spin. And then one has to impose the GSO constraint, which means locality with respect to the space-time supercharges. And once we have this, we are almost there. There are two additional constraints. And the first constraint comes from study of strings in ADS3 by Marisa Naguri, which showed that the ADS3 spin for discrete states have to be bounded between half and k plus 1/2. And secondly, if you want a unitary theory on Y, then the dimension of this operator on Y has to be bounded by the central charge of the theory on Y. So there are two inequalities. And if you go through the details, what we showed is that the only way to get boundary chiral ring elements is if the operator on Y has to be either a chiral primary, I mean a worldsheet chiral primary, or a worldsheet anti-chiral primary, or a Raman-Raman ground state of the theory Y. Okay, so I mean, previous works have seen this for various cases, but without any assumptions, we have just shown that this is an if and only if statement. So this is one of the results of our work. So given all this, here is a list of operators at zero spectral flow, and we can also do this with spectral flow. There's no problem. So you can see that there are two types of operators in the NS sector of the worldsheet theory, and a different kind of operator from the Raman sector. And this is the boundary conformal dimension of these operators. So the first step is done. We have obtained the BPS spectrum at zero spectrum. Okay. Any questions? Once we get the spectrum, then yeah. Was that a question?
No, you continue.
Okay. Sure. So what can we expect for the chiral ring? So the work on the chiral ring goes back to the classic paper by Ayan K, and Warner. So if you take a general operator product expansion of two fields in the boundary CFT, you will find something that looks like this. But because I have a chiral ring element, charge conservation of the U1R charge conservation ensures that the OPE or the operator product expansion is completely regular. So what we want to find is a C1, 2, 3. Another point that I'll come to at the end is the fact that the chiral ring has been shown to be topological by work by Cecotti and Waffa. So one expects these structure constants to be determined by the topological data of the worldsheet theory on Y. And for n equals 4 models, what people did was to compute physical 2 and 3 point functions and then take ratios to read off the chiral ring. So here what we're going to do is do directly the OPE from the worldsheet CFT. Okay. So one complication is the fact that because we have these picture numbers and so on in the superstring, we have to not just find these operators. So here I've written the operators in the canonical picture. So -1 in the NS sector and -1/2 in the Raman sector. If you want to find the OPEs, then we also have to know these operators in the other pictures, in picture number 0 and also picture number -3/2. So this we can do. So for instance, one of these NS operators in the 0 picture looks like this. It's some currents acting on these or some descendants of the fields in Y. So it's complicated, but it can be done. So once we have all this machinery in place, let's compute the OPEs. Now, the OPEs in the S1 direction, the fermionic direction, this goes, all of these are standard, they're all found in textbooks by now. So the only non-trivial part is really the OPE in the ADS3. And the OPE in the ADS3 looks like the following. So this is from Teschner. Should I give a reference? I'm Sorry about that. But again, once we impose the fact that I'm in a chiral ring, then it turns out that really the only OP one need is completely trivial. So when the H3, when there's H on the right-hand side is the chiral ring element on the right, in all but one case of OPs that we will calculate, we'll get a trivial OP in the ADS3 sector as well. So really the only missing ingredient is a set of OPs in the Y sector. And this is something that we did from scratch because we couldn't find these OPs anywhere in the literature. But again, the idea is very simple. You start from the world sheet chiral ring, which is just what I've shown here in this equation. And this is determined by the structure constants of the world sheet theory on Y. I don't know what they are, but they're some R. Given this and given the spectral flow, which is guaranteed because of the 2,2 superconformal symmetry of the Y theory, we can determine all the others because the Raman ground states and the antichiral primaries can all be obtained by spectral flow by half or 1 unit on the world sheet. So for instance, I've just given you sample OPs for chiral ring and Raman ground state or chiral ring with chiral ring element with the antichiral ring element. You'll see that it's a bit complicated, but it's really quite simple at the end. So here, the coefficients now depends upon not just the chiral ring, but also on the homological metric, which is actually non-topological data. So it'll be one of the interesting things that we'll see is how, at the end of everything, the space-time chiral ring indeed depends only on topological data. So that's one thing to look out for. So now we also have the OPs in the Y sector. So how does one do an OP? So again, this is textbook material. If you open the yellow book on conformal field theory, you'll see that if you have composite operators, you use the generalized Wick theorem. So we have these operators where you have current times and primary OP with a primary. So you just do it successively, and it's just standard OP techniques. Okay. So now let's come to the only subtle point in the evaluation of the OP. So what we get is the following. So because I have a zero ghost operator in the NS sector, for instance, I have an integral over the insertion of one of the operators. Then the ADS3 OP will lead to an integral over these intermediate ADS3 spins. I have some worldsheet dependencies and all these operators here. And the boxed element is some differential operator that acts on this phi j element. This differential operator not simply on the worldsheet, only on spacetime. Now, what we find is that in the limit of the spacetime OP, so now I take the limit that x1 goes to x2, where these are the two boundary points of my collidic fields. Then what we find is that the only contributing element or the leading element, the leading term that contributes to this OPE fixes the ADS3 spin to be exactly that for a propagating mode. Okay. And once you set that in, all of these things essentially collapse to a chiral primary on the right-hand side. Okay, so I'll say this again, and this is a point that was made by Aharoni and Kovnagotsky back in 2007 or 2009 maybe, where they were also trying to derive the spacetime OP from the worldsheet OP, and they found that in the spacetime OP limit, the dominant contribution to this worldsheet integral arises from on-shell states. So in the J integral, this essentially amounts to doing a residue calculations, and the result is a chiral primary at the end. Okay. So given all the NS sector and the Raman sector fields from the worldsheet, we can do this for all possible OPs that can exist, and we can use the same trick of this worldsheet to spacetime OP, and the answer is extremely simple. So what we find is that there is in all but one case, we get a universal coefficient that depends on the conformal dimension of the field on the right. So H3 is something like H1 plus H2 minus 1. And everything that appears on the right-hand side is purely topological. So it's either a structure constant of the worldsheet theory on Y, or it's what is called the topological metric by Chakotay and Waffa. And to do this, what we did was a simple change of basis from what we did. So we redefined one of the operators. And once we did that, we see that all the OP coefficients is purely topological. So this is what one would expect naively, and this is what one finds. So whatever Y is, what we are saying that the OP coefficients looks exactly like this. Okay, now let me come to the only non-universal contribution to the OP. And this arises because of this ghost number business. So because of this zero ghost term, zero ghost operator, one of the contributing terms for one of the OPs involves a descendant of the primary on Y. So this is a non-universal contribution, and this we cannot know what it is unless we work out explicit models. So again, we went back to those two particular models that we had, the n equals 4,4 case, and this n equals 2 theory, which is a sum of 3 minimum models. So here Y is sum of 3 minimum models. And we try to evaluate what this OPE should be in that case. And we again find a surprise. What we find is that the structure constant is, the methods are the same. And now we find a non-trivial product of two OPE coefficients, one from the ADS3 factor and one from the SC2 factor. But again, because once you impose the chiral primary condition, what we find that it's again a constant. So in a way, it's disappointing. I'm not sure what I'm not sure we understand what this means. And I'll discuss whether this implies a non-renormalization theorem or not at the end. It's not clear if such a cancellation occurs for all Y. It's highly unlikely, in my opinion. But for the universal class, for a large class of OPs, the result is indeed universal. Okay, I hope this point is clear. So now let me comment on the results. So one important point to make is that we did not compute the OPEs in the in the spectral flow non-zero sectors. Given that, so assuming that we can do that, suppose we set this combination h minus 1 plus kw to be some n, some integer n. Then what we can check is that this coefficient 2h3 minus 1 in terms of this n becomes n1 plus n2 minus 1. Okay? And this is the same combinatorial structure constant that arises in the study of symmetric orbifold CFTs by Lunin and Mathur, where these NIs have the interpretation as these lengths of permutation cycles in the symmetric orbifold confounded field theory. Now, for the n equals 4 models, there is a non-renormalization theorem that has been proved by DeBoer et al. That shows that these structure constants of chiral ring operators are covariantly constant on the moduli space of this n equals 4,4 theory. So whether we compute it in the worldsheet theory or whether we compute this in the space-time theory, in the symmetric orbifold point, they should match. So for 4,4 theories, there's a non-renormalization theorem that makes full use of the full n equals 4 algebra. And so this match between this and the symmetric orbifold is not a surprise. But for us, it is a surprise because for n equals 2 theories, the structure constants do change. They satisfy these TT star type equations of Chekhov and Waffa. And it's not clear why we again find this, these combinatorial factors. And more surprisingly, for the two specific examples, well, for the one non-trivial n equals 2 examples that we studied, we again, for the non-universal factor, we find this n1 plus n2 minus 3 coefficient in that case, which again suggests that there should be some symmetric orbifold interpretation, but why they should match under deformation to go from the symmetric orbifold point to any other point is not clear to us. So this is gives rise to lots of questions. Will this hold for other models? We don't know. Does this imply or suggest some non-renormalization theorem for n equals 2 models? I don't know, but the only calculation that we can do indicates that there is some relation to a symmetric orbifold dual. So with that, I'll stop and I'll take questions. Thank you.
Thanks, Sujay. Questions? If you can raise your hands, I can go one by one.
Yeah, I can't see the screen very well. So yeah, maybe it'll be good if you can tell me.
No, it's okay. I will coordinate. Souvik Datta has some question. Can you unmute and talk? Yeah.
Yeah. Hi. So thanks for the nice talk. Sorry. So actually, the examples which I was mentioning is for those dual CFTs which we had, those were actually symmetric orbifolds.
Okay.
Yeah. So usually for the 4,4, you have the symmetric orbifold of T4, or say that symmetric orbifold of K3. But for the 2,2 case, you take you orbifold the T4 first in some way, and then take the symmetric orbifold of that.
Okay.
So so I mean, probably there is some relation with this.
For the 𝗰𝗵𝗶𝗿 theory in our formulation, the Y theory is, for instance, T dual to a minimal model times T4, and the symmetric outfold is just of the T4, not of the minimal model. So in the general case, it's not clear to me what exactly our symmetric outfold, but it's a good question to think about. Yeah. I don't have an answer.
And also, can one say something generally about the elliptic genus of this of these theories?
Yeah, it's a good question. I don't have anything to say in this talk, but yes, one should be able to. I think yes, there are papers by Alejandra Castro and so on, I guess, who do.
Yeah, but for those cases, there wasn't a precise identification with the bulk dual. But since you have something more precise here, probably.
We have not tried to do that, but yeah, it's a good question. It's definitely.
Thanks.
Anyone else? Because I don't see any raised hand. I think Shauvik's hand is the old hand. Okay. Okay, so let's thank Sujay Ashok for this nice